My name is Alejandro Hevia. I'm a professor at University of Chile. I'm the head of the Random Chile project, which is a randomness beacon that we have here in Chile. There are a lot of people behind this project, so I would like just to thank Camilo Gomez, who is the lead developer, but there's many people doing the fantastic job here, so it's just not me. So I was asked to talk about some applications. I would like to tell some applications of public randomness that we have developed in Chile. So even though they use our beacon, the idea is that they could use something like the League of Entropy, actually randomness generated by Drand or something like that. So just a quick head up here about what we are. We are essentially, we started working in 2017 to try to create somehow an extension of try to replicate and extend the randomness beacon by NIST, but with a particular goal was to provide transparency and trust to digital services that rely on randomness, okay? Our idea was to use this in a way to provide transparency to some processes. And this is something we would like to talk here. I think Luke mentioned it before, but just a point is that our beacon, although it uses a similar approach as the one by NIST, we have a different way to generate randomness in the sense that we sample different sources. Particularly, one of them is the source from earthquakes. So that's why the seismic girl is standing on top of the earth moving. So we like that pretty much. And so let me just go into the point right away. Since the motivation was to provide transparency, we decided to look into places where transparency was an issue, in particular with randomness. And in Chile, we do have, as in most countries, we have an agency which is in charge of auditing the expenditures of taxes, you know, how government spend taxes, whether they actually do it following all the regulations and in proper ways. Here in Chile is called Contraloría General, which for people in the US, it would be something like the Comptroller General. This is the independent agency in charge of preventing essentially politicians to mismanaging the funds. And what they do is they actually do a random selections of people, of government officials for audits. And the main problem they had for a long time was that, of course, they don't have enough funding to do audits in every single government official. So they had to pick people at random. And because of the process was not really that transparent, they were frequently accused of political persecution. So for them, when we approached them to tell them, look, you can do this in a verifiable way, they were really excited because that would be a way to provide more transparency to the whole process. So you guys have an idea how this works. The main idea, this is one case, but the main idea in this particular case is that you have a process in which you have a universe, a list of all possible government officials who could actually be subject to audit. And the idea was to select some of them at random. Of course, in practice, it was a little more complicated, but the overall idea was that we managed to create a way in which we could take some of these inputs and make them public, make this input in public here. And somehow the whole selection process was being done outside of this agency using the output of a particular pulse from the beacon, or particularly it could actually be a particular day. For what exactly happened here is that the Contraloría actually commits to perform this selection, say on January 1st to noon, and on that day it just provides all the inputs in a website, and the selection is being done with the pulse, with the randomness from the pulse of that particular date and time, and the output actually is also public. And the whole process is designed in a way that you can recompute it, okay? Again, any external observer can recompute it. So that's quite an interesting aspect to do the verification. Of course, there are many details. The selection needs to be done in a way with is based on in a particular number, which is called the risk factor. And the risk factor, there's several buckets of risk factor. So there is a little more complicated selection, but it can all be done and actually could be recomputed by any external observers, provided that they know exactly when this took place, so they are able to recover whatever randomness was generated in that moment and recompute. There are more details, and the more detail is that this is the most basic aspect of the selection. There's some other selection that requires to use data which might be sensitive. So you might have some private inputs. Let's say sometimes the risk factor associated to a particular government official is based on other data. Let's say how much money they make, whether they have properties or not, and that information might be sensitive to reveal. You cannot reveal it. So we have a second solution in which you use commitment and using some range proofs to prove that people belong to a particular bucket of risk. So you can actually select it with a certain distribution there. So we did that. Unfortunately, this is a project that's been on hold at this moment because, of course, like everyone in the world, we are going through this pandemic, and this is, we hope to resume this project soon. But actually, one of the key issues here is that the process to provide transparency is even though it may be simple initially, providing transparency when you have private input requires some testing because you need to convince people what we are doing is correct. And we believe that according to our initial prototypes that we're actually doing it. And there's a second application that we have is that to be able to, with the Electoral Service in Chile, you probably don't know, but in Chile, the poll workers are not government officials, so they have to be selected by, they are selected at random among all the citizens who are able to vote. And of course, that for a long time, there was a source of controversy because people were complaining that they were selecting again and again, and the process was not really fair. So we use the public randomness to actually provide a more transparent process there. And in a more interesting application is that in a project, in an initiative that is being done with the Chilean Congress, we created a particular scenario in which this is called Deliberative Convention. Is an idea from political science, actually from Professor James Fishkin from Stanford, to invite random citizens to get together and to talk about a policy, some policy options about, medical care, some policy related to the country. And the idea is to bring a subset of all citizens to discuss about this issue, and hopefully, since it's a random selection, the output of this discussion is more representative for the country. And we actually, this is something that has been done in other countries, in the US, in Europe. This is for the first time will be done here in Chile, and our participation is to provide the random selection of the citizens, which is actually a way to everyone to get convinced that this is a fair process, and every people in the country has the same chance to participate. There are some smaller projects that we are working on. Just to mention a few, as mentioned before, to be able to audit elections, risk-limited audits. We have some interesting project with private randomness to try to provide verification of a certain process without really revealing the randomness being used in a way that's more specialized. And of course, some of the other projects you have discussed it here before about using in consensus algorithm and so on. So I'm pretty happy to answer some questions later, but our goal here, just to mention, there's uses here of randomness, which are very, in my opinion, very important for the transparency of certain processes, especially those which involve decisions that affect a large collection of people. And we believe there is plenty to do there. So thank you. I think on this, I will have to yield to Wayne, I think.
Thank you. Hello, everyone. My name is Wayne Vaughan. I'm the CEO of Tierion. We work on a project called Chainpoint, which allows you to create a timestamp proof that anchors to the Bitcoin blockchain. So when we were launching a new version of the protocol back in 2017, we wanted to find a way to be able to prove not just the existence and integrity of data, but also provide some strong evidence of when the proof itself was created. And so just to kind of give a quick overview of the way Chainpoint works, you take a hash of some data, you send it out to a gateway on the network, you get back a V1 UUID, and at some point in time in the future, after a bunch of magic happens in the background, you'll be able to get back a timestamp proof that has a commitment to, or is anchored to the a block on the Bitcoin blockchain. And so what we, and just for some context, the way that people use this is for things like document timestamping, being able to prove that data that's collected during clinical trials hasn't been manipulated, those types of use cases. So, so what we wanted to do was not just prove the existence and integrity of data, but we also wanted to be able to prove when a proof was created in a certain time window. So what we did is we started injecting the NIST randomness beacon into our into every Chainpoint proof. And what that allows you to do is essentially you're able to verify that it provides, you know, proof is maybe too strong of a word. It provides pretty strong evidence that your proof was created after that randomness, the pulse from the NIST randomness beacon was generated, because you could never know the value in advance. So we ran this system for about, I'd say about 2 years. And, you know, thousands of nodes on the network, lots of organizations using the technology. But we did notice some things, some problems with using the NIST randomness beacon. Number one is that sometimes it went down. You know, there were intermittent outages. It didn't really impact the core ability that we were delivering to users of the network. But, you know, it did bother us. And then secondly, we noticed that the NIST randomness beacon, the software development on it seemed to slow down. And at one point in time, NIST published a document that said, hey, if you're gonna make a randomness beacon, here's some of the properties that this randomness beacon should have. So that became a signal for us to look for something else. And after lots of evaluation of different options, we settled on using Drand and became a member of the League of Entropy. And there's a couple of advantages from switching from the NIST randomness beacon to using Drand. So number one, it's permissionless. We didn't have to ask anybody for permission. We simply evaluated the technology, downloaded the software, started running our own Drand node. And as of July 9th, 2020, every Chainpoint proof from our systems is concluding a Drand pulse instead of a NIST randomness beacon pulse. So it's permissionless, and then also the NIST Drand, the Drand beacon issues a pulse every 30 seconds, whereas the NIST issues a pulse once per minute. So although time precision and accuracy is not important for our use case, it is an added benefit that we're getting basically double the time precision for the from Drand. So you know, essentially, you know, we were able to join the network. We get double the time precision. It was a no-brainer for us. So we set up a NIST Drand node, and we're planning on running 3 in the future. And it was very, very easy for us, and didn't really take any time at all. So if you want to learn more about Chainpoint, you can go to github.com/Chainpoint and learn about what's there. And I want to thank everybody for asking me to come and talk a little bit today about what we're doing.